This PowerPoint goes along with Newton's Laws example problems. These are a few questions that come out of the OpenStax textbook, chapter 4 and 5. In chapter 4 it says, for number 5, figure 4.7 below, which is this figure right here, the net external force on 24 kilogram mower is stated to be 51 newtons. So we're talking about basically a horizontal force because the upward and downward forces are going to be canceled. They're going to be balanced. If the force of friction opposing the motion, which is 24 newtons, what is the force that the person is exerting on the mower? Suppose that the mower is moving at 1.5 meters per second. When the force is removed, how far will the mower go? All right, so for the first part, what force is the person exerting on the mower? Now, from the picture, it looks like he's actually pushing downward at an angle, and I know that's what it appears to be, but nowhere in the problem does it say that he is pushing at an angle. It doesn't state the angle. So we're going to assume that he has a horizontal force that he's pushing on the mower with. Alright, so that gives us our free body diagram to be the normal force upward, the force of gravity downward, force of friction is opposing the direction of motion, so we got a horizontal force that he's pushing on it with. So the net force in the x direction is going to be force 1 that he is pushing with minus the force of friction equals 51 newtons. Now we plug in 24 for the force of friction, add that to both sides, and we get that the force that he has to be applying is going to be 71 newtons. Now the second part of this says, suppose the mower is moving at 1.5 meters per second when the force F is removed. So the force that he's applying is removed. How far will the mower go before stopping? Alright, so we know the initial velocity is going to be 1.5 meters per second. We know the final velocity is going to be 0 because it's going to stop, and we're looking for how far it's going to go, and we can use the net force in order to figure out the acceleration. Now for the free body diagram for this new problem means that force 1 is going to be eliminated. He lets go of it, so we only have force of friction in the horizontal direction. So net force in the x direction equals negative force of friction. That equals mass times acceleration. Well, the force of friction was already stated to be 24, and the mass is 24, so we're going to divide both sides by 24. We're getting acceleration at negative 1 meter per second squared. So we got the final velocity, we got the initial velocity, we have the acceleration. We're looking for displacement. We're going to use this equation: final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Plug in our numbers, then solve for the displacement. So we take 1.5 squared and then divide by this 2 times 1. So divide by 2 and we get displacement is going to be 1.125 meters. The next problem, number 7, it says, part A, if a rocket sled shown in figure 4.32, which is this one right here, starts only one rocket burning, what is the magnitude of its acceleration? Assuming that the mass of the system is 2,100 kilograms, the thrust for all of the rockets is 2.4 times 10 to the 4th newtons, and the force of friction opposing the motion is known to be 650 newtons. Okay, so looking at just the horizontal direction, it's pretty simple, so I didn't draw a free body diagram. We only have the thrust, that's 1/4 of the thrust actually, minus the force of friction equals mass times acceleration. So I take 1/4 of 2.4 times 10 to the 4th minus 650, because that's the friction. It's going to be equal to 2,100 times acceleration. Calculate that out, we get acceleration is 2.55 meters per second squared. Now part B asks, what is the acceleration, or why is the acceleration not 1/4 of what it was with all the rockets burning? And that's because the thrust is divided into 4, but we still have the full amount of friction. If we look at the equation, the thrust is divided by 4, but not the friction. The friction is going to be 650, whether all the rockets are thrusting or only one is going to be thrusting. So that means the acceleration is actually going to be a little bit less than 1/4 because we have the full force of friction. If we divided the force of friction by 4, then yeah, we'd have exactly 1/4. But since we have the full force of friction, it's going to be a little bit less than 1/4. Number 17, also in chapter 4, it says 2 teams of 9 members each engage in a tug of war. Each of the first team's members has an average mass of 68 kilograms and exerts an average force of 1,350 newtons horizontally. Each of the second team members have an average mass of 73 kilograms and exerts an average force of 1,365 newtons horizontally. What is the magnitude of the acceleration of the 2 teams? Okay, first of all, we kind of have this nice little diagram. Didn't really take too much time to put into this, but this is the first team over here. This is the second team over here. Team A is going to be the 73 kilogram members, and then Team B is going to be the first one, which was 68 kilogram members. Alright, so we got a force of tension inside the cable, and then we got each team pulling its opposite directions. Okay, we have an acceleration. Obviously, the team A is going to have the direction of the acceleration because they're pulling with more force each. Each one's pulling with 1365, and team B is each pulling with a force of 1350 newtons. So obviously, this one over here is going to win the tug of war. All right, so we define our system. We're going to make the tension inside of our system, since we technically don't know what that is. So we got the force that the first team is pulling to the left, and then the second team pulling to the right. So the net force is going to be equal to the force from team A minus the force from team B, and that's going to be equal to mass times acceleration. Well, each member is pulling with 1365 from team A times 9, and then each member from team B is 1350, multiply that times 9, so each person pulls with that amount, so we multiply by the number of people on each team. And then we have 9 times 73 and 9 times 68 because that's the total mass of all of them. So 73 plus 68 and then times 9. So basically one member from each team and then multiply by 9 because each team has 9 members. Solve for the acceleration, and you get acceleration is going to be 0.106 meters per second squared. Now this brings us to part B. It says what is the tension in the section of the rope. So what is the tension here? So we're going to define our system as just team A this time. So we have team A minus the tension is going to be equal to mass times acceleration. Plug in what we have. We have force A is 9 times 1365 minus tension. It's going to be equal to 9 times 37. Now we're just dealing with one team, so it's a 73 kilograms, then multiply by the acceleration because the acceleration of the entire system is constant. All right, plug it in, and then find the tension to be 12,215 newtons. Now, if you redefined your system as just team B, you should get the same answer. Next question in chapter 4, number 35 says a nurse pushes on a cart by exerting a force on the handle that is downward at a 35-degree angle below the horizontal. The loaded cart has a mass of 28 kilograms and the force of friction is 60 newtons. Part A is to draw a free body diagram of the system of interest. So we have the force that's being acted on by the nurse. We have the upward normal force from the ground holding the cart from falling. Then we got force of gravity downward. And then the force of friction is horizontal, preventing its motion. Alright, so part B says what is the force that the nurse must exert to move it at a constant velocity? That means no acceleration in the horizontal direction. So the component of force 1, which is the force she's applying, that is horizontal, so that's going to be cosine, the cosine component of force 1 minus the force of friction back in the other direction is going to be equal to 0. So we rearrange this and we get that force 1 is going to be equal to the force of friction divided by cosine of the angle, and then we punch that in and we get the force 1 is going to be 73.2 newtons. Number 39 in chapter 4, part A, it says, what is the initial acceleration of a rocket that has a mass of 1.50 times 10 to the 6 kilograms at takeoff, and the engines of which produce a thrust of 2.00 times 10 to the 6 newtons? Do not neglect gravity. This is a question that actually talks about unintentional results, so something you don't actually want to happen. So we start with the free body diagram, the thrust upward, the force of gravity downward, and then we do our Newton's second law, net force in the y direction equals the force of thrust, which is upward, minus the force of gravity, which is downward, and that's going to be equal to mass times acceleration. So the thrust is 2.00 times 10 to the 6 is given in the problem, minus mass times gravity. The mass is 1.50 times 10 to the 6 times 9.8, and then that's going to be equal to the mass of our system, which is the mass of the rocket, 1.50 times 10 to the 6 times acceleration. So we punch this in and divide both sides, and we get our acceleration is negative 8.47 meters per second squared. Now part B asks, why is this, or what is unreasonable about this result? Well, if you want a rocket to take off and an initial velocity is 0, it's just sitting there, then you want the acceleration to be positive because it has to move upward. So the rocket is supposed to have a takeoff that is upward, and the initial velocity being 0, the rocket needs to have an acceleration that's upward, so a downward acceleration means it's going to crash. Part C, which premise is unreasonable, or which premises are inconsistent? Essentially what we're looking at, one of two things are happening. Number one, either the mass is incorrect, it's too high, or the thrust is too low. So we need either more thrust or we need less mass, depending on which situation this problem pertains to. All right, number 46 in chapter 4, it says a basketball player jumps straight up for a ball. To do this, he lowers his body 0.3 meters and then accelerates through this distance by forcefully straightening his legs. This player leaves the floor with a vertical velocity sufficient to carry his feet 0.9 meters above the floor. Part A, calculate his velocity when he leaves the floor. So when he leaves the floor, he's going to move upward. After leaving the floor, gravity is going to be slowing him down. He's going to be moving upward until he stops at the very top, which is 0.9 meters above where he started. So if his initial velocity is what we're looking for, then his final velocity is going to be 0, and the acceleration as he's moving through the air, gravity is pulling him and slowing him down, so it's negative 9.8, and then he's going to be moving upward 0.9 meters. Alright, so crank this out and you get the initial velocity is going to be the square root of 17.64, and that gives an initial velocity of 4.2 meters per second. Continued on this problem, part B, it says calculate the acceleration when he is straightening his legs. So during the part of his jump that he is moving 0.3 meters above where he started. Well, we already figured out that when he leaves the floor, he's moving at 4.2 meters per second. And when he starts pushing himself upward, he's moving at 0 meters per second. So we know his initial velocity, we know his final velocity, and we know his displacement. We're looking for acceleration. So we're going to use this equation again. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Plug in the numbers that we know, solve for acceleration, and we get the acceleration is 29.4 meters per second. Now something interesting about this that we should notice is that this is 3 times the acceleration due to gravity. Gravity is negative 9.8 meters per second squared. Now if you look at how far he moved, which was 0.3 meters, and how high he jumped, which was 0.9 meters, his height jumping was 3 times what it was in order for him to stretch his legs, which kind of makes sense since the acceleration due to gravity as he was off the floor is 1/3, then he had the same velocity, went from 0 to 4.2 in 1/3 the displacement with 3 times the acceleration. Alright, part C says calculate the force he exerts on the floor to do this, given his mass is 110 kilograms. We draw our free body diagram where his force upward minus the force of gravity downward is going to be equal to mass times acceleration. Force of gravity is mass times gravity, so we plug in those numbers, solve for force 1, and we get 4,312 newtons as the force that he applies. Alright, moving on to chapter 5, it says calculate the deceleration of an 87.0 kilogram snowboarder going up a 5.0 degree slope, assuming the coefficients of friction for waxed wood on wet snow, which is coefficient of static friction 0.14 and coefficient of kinetic friction 0.10. Be very careful to consider the fact that the snowboarder is going uphill. So we need to know that his velocity, his initial velocity is up the hill, which means friction is going to be pushing him back down the hill. If he's just sitting there and then gravity's pulling him down the hill, then friction is going to be back up the hill because it's trying to slow him down. Alright, so force of friction is down the hill. So we have a component of gravity that's perpendicular and a component of gravity that's parallel to the snow-covered hill. So we look at the force of the net force in the x direction. So we're looking at parallel to the ramp, parallel to the hill. So we got negative force of friction. So I made down the hill negative and up the hill positive, primarily because the velocity is up the hill, so I made that direction positive. Really doesn't matter. You can make either direction positive or negative. You'll still come up with the same answer. So we got force of friction in the negative direction minus the component of gravity that is also in the negative direction. If we look at this component of gravity that's back down the hill, which we've identified as negative, that's going to be equal to mass times acceleration. Alright, the force of friction is going to be equal to the coefficient of kinetic friction times normal force because we are sliding, minus mass times gravity, sine of theta, and that's going to be equal to mass times acceleration. And again, up front, that coefficient of friction times normal force was negative. Alright, well we don't know the normal force, so we're going to have to look in the y direction. So we need the net force in the y direction. That's going to be equal to normal force minus the component of gravity that is perpendicular to the ramp, and that's going to be equal to 0. So solving for our force of gravity, for our normal force, we get mass times gravity cosine of theta. Now if you want to, you can plug in the mass, you can plug in gravity, you can plug in that angle and get a number here, but I'm not going to do that, and I'll show you why in just a second. I'm going to plug it in for normal force. So I get negative coefficient of friction times this normal force, which is mass gravity cosine of theta, minus mass gravity sine of theta equals mass times acceleration. Now something you may notice here is that each one of these 3 terms all have mass in it. So actually the fact that they're 87 kilograms really doesn't matter because that's going to cancel out of all of them. So then acceleration, which is the only thing left on this side, is going to be equal to negative coefficient of kinetic friction times gravity times cosine of the angle minus gravity times sine of the angle. Plug in our numbers, we get acceleration is going to be negative 1.83 meters per second squared. And since we said down the hill is going to be negative, then that means the acceleration is going to be down the ramp. The next question, number 11, part A says calculate the acceleration of a 92.5 kilogram skier heading down a 10-degree slope, assuming the coefficient of friction for waxwood and wet snow, which we've already had in the previous problem. The coefficient of static friction 0.14, the coefficient of kinetic friction is 0.1. Alright, so this time we have friction going in the opposite direction because now he's going down the hill, so the friction is upward. And I'm going to go ahead and make down the hill in this problem, I'm going to make that the positive direction. Alright, so to find the, let's see, we're calculating the acceleration, so the acceleration's in the x direction, so we need the net force in the x direction. That's going to be equal to negative force of friction plus mass times gravity, which that would be the force of gravity, sine of the angle. Sine, because we're looking at that x component of gravity. Force of gravity, sine of the angle is going to be equal to mass times acceleration. So we get for friction is coefficient of kinetic friction, since he is sliding, times normal force, plus mass times gravity, sine of the angle. That's going to be equal to mass times acceleration. Again, we need to find the normal force. Now this looks a lot like the previous problem. The only difference is now friction is the opposite direction because we're moving down the hill this time. The previous problem we were moving up the hill. So friction had to change direction in this problem. Alright, so to find the normal force, we look in the y direction, so net force in the y direction is going to be equal to normal force minus the force of gravity cosine of the angle. Rearrange that and we get the normal force is equal to mass times gravity cosine of the angle. Plug that in, and again you should notice that we're going to have mass cancel out of each one of these. So acceleration is going to be negative coefficient of kinetic friction times gravity times cosine of the angle plus gravity times sine of the angle. Plug those numbers in, we get our acceleration is going to be positive 0.737 meters per second squared. Now at the beginning of the problem, again, we said that down the hill was positive, so because it's positive, this is going to be down the hill as well. Part B says, find the angle of the slope down the hill with a skier that could coast at a constant velocity. And that means that the acceleration is going to be equal to 0. So we're going to go through the same scenario pretty much. We're going to go through all this math again, but basically come back to this equation where acceleration equals 0. So we need to find the coefficient of kinetic friction where acceleration is going to be 0. Alright, so we plug in 0 for the acceleration. That gives us this part over here. We need to isolate that coefficient of kinetic friction. So we're going to bring all of this to the other side. Notice that gravity is going to cancel out because we divide both sides by gravity, which is not equal to 0, and 0 divided by gravity still gives me 0. Bringing this to the other side becomes positive, and then we're going to divide by cosine. Bringing this part right here to the other side just leaves sine of the angle. If we bring this over, it becomes positive, divide by cosine, we get sine of the angle divided by cosine of the angle, which we know is tangent of the angle. Now in order to find the angle, we got to take the inverse of both sides, inverse tangent of both sides, and inverse tangent of 0.1, since it is sliding, that's the coefficient of kinetic friction that we're dealing with, and we get that the angle is going to be 5.71 degrees. So at a 5.71 degrees, they'll slide at a constant speed. Now that is assuming they're already sliding, because if they're not already sliding, then the coefficient of static friction will take over, and you need actually more force in order to begin to start moving, but once it starts moving, you only need an angle of 5.71 degrees. To get it to start sliding, you would need an angle that's greater than that, just a little bit. In this problem, number 17, it says, consider the 52 kilogram mountain climber in figure 5.22 below. Find the tension in the rope that the force that the mountain climber must exert with her feet on the vertical rock face to remain stationary. Assume that the force is exerted parallel to her legs. Also assume negligible force exerted by her arms. So we're assuming that the force that her arms, or that basically the tension's coming straight from here and she's just kind of resting her arms there. We have a force from her legs. Now this is a little confusing. We'll get to this in a second because the force is being applied to the rocks here. But if you notice, something you should notice here is that this actually is going to have friction with her feet, and then there's a normal force outward, and those two forces what supplies the force to her feet that her legs get to use. Alright, so drawing our free body diagram, we're going to include all of this except her feet. So her legs are an outside force pushing on her body. So if we draw the free body diagram, we got her legs pushing out, we got the tension of the cable pulling up, and then we got force of gravity downward. Now technically the force of gravity is not the entire 52 kilograms because the way we drew our free body diagram, we're kind of leaving out her feet. Well, let's just assume that that amount of mass is negligible. Let's just consider that an arbitrary omittance. Alright, so looking in the x direction, we got the force from her legs cosine of the 15-degree angle, so that's the horizontal component, minus the force of tension sine of 30 degrees, so that's the horizontal component also, and that's all the forces in the x direction. Now we want her to be stationary, to remain stationary, which means not moving and not accelerating, so the net force is going to be equal to 0. Alright, so rearrange this. The force that her legs are going to be applied, we bring this negative tension times sine of 31 to the other side, and then divide by cosine, and that gives us this part right here, which is about equal to 0.533 times the tension. Alright, well that gives us the x direction, but we got two variables, so we need another equation. We go to the y direction and look at the y component of tension, which is cosine of 31 degrees, and then the y component of the force being supplied by our legs is sine of 15 degrees. Minus the force of gravity downward is going to be equal to 0. So we plug in our numbers, we rearrange a little bit here. The force from her legs, well, we already found to be 0.533 times the tension, so we plug that in here. And then the force of gravity is mass times gravity. Alright, so go ahead and figure this out. We got cosine of 31 degrees, sine of 15 times 0.533, then we add those coefficients together to get our tension, and then we got mass times gravity, which is 52 times 9.8. Take that part to the other side, it's 509.6, and then these two coefficients here added together gives us 0.995. Divide both sides, and we get the tension in the cable is going to be 512.1 newtons. Now Part B is wanting to figure out what is the minimum coefficient of friction between her shoes and the cliff. So now we need to look at just this part right here. Now this gets a little confusing because you're thinking, well, that force right there is the force of the legs. Well, we're not looking at the force of the legs, we're looking at the force on the feet, and the feet are applying a force this way. The feet are applying a force that way. So we have a force from the legs on the feet that's down in the opposite direction. So this system over here had the force from the legs up and to the right. This force down here has the opposite force, which is down and to the left, and that's because of Newton's third law. Alright, then we got a normal force. The rock face is pushing out on the feet and pushing up on the feet with a force of friction. So we got force of friction upward, normal force perpendicular to the surface, which is outward, and then the legs are pushing the feet into the rock face, and that gives us our force there. And this gives us our free body diagram for a system in equilibrium. Alright, looking in just the x direction, net force in the x direction equals normal force minus the force of the legs, cosine of the angle, so that's the x component, and that's going to be equal to 0. So the normal force minus the force of the legs cosine of 15 degrees, and that pretty much takes us down to all we can do right here. Now on the previous example, in Part A, we found the force of tension. We could actually use that to find the force of the legs, but you'll see in a second that that really doesn't matter because this will actually cancel out. So let's look in the y direction. The net force in the y direction equals the force of friction minus the force in the legs sine of 15 degrees. So we're looking at the vertical component of the legs, and that equals the force of friction. So those two are balanced, and we get those equal to each other. Now in order to find the coefficient of friction, for static friction, the force of friction is less than or equal to the coefficient of static friction times normal force. Now taking the normal force to the other side, we get coefficient of static friction is going to be greater than or equal to the the force of friction divided by the normal force. And that equals, well, force of friction is force of the legs sine of 15 degrees. The normal force is force of the legs cosine of 15 degrees. You'll see the force from the legs are actually going to cancel. Sine over cosine gives us tangent, so the coefficient of static friction is going to be greater than or equal to tangent of 15 degrees, and that gives us 0.268. So the minimum coefficient of friction that it can have is going to be 0.268.